Hey everyone, and welcome. All around us, every single second, the world is changing. It's this silent, kind of invisible process of transformation happening in everything from the food we eat to the air we breathe. So today, let's pull back the curtain on this hidden world of chemistry together. So to get started, let me ask you something. I want you to think about these three things: a nail that's slowly turning to rust, a cake rising and browning in the oven, and one of those antacid tablets just fizzing away in a glass of water. On the surface, they seem completely different, right? But believe it or not, they all share a secret connection. And that secret is, they're all chemical reactions. This is the hidden engine that drives almost every single change you see, and even the ones you don't. It's basically how stuff becomes, well, different stuff. Okay, so let's get down to it. What exactly is a chemical reaction? Let's get a really clear definition on that. So a chemical reaction is basically any process where your starting substances, we call those reactants, go through a change to become brand new substances, which we call products. And the really key thing here is that these products have completely different properties than what you started with. It's all because their internal chemical bonds get broken apart and then rearranged into something new. You can really just think of it like a simple before and after story. In the before picture, you've got your reactants. Those are your ingredients. Then the reaction happens, and in the after picture, you get your products, totally new substances. You might start with a solid piece of metal and a clear liquid, and you end up with a dissolved salt and a fizzing gas. It's a total transformation. Now, as you can imagine, chemists don't just write out these stories in long, boring sentences. No, they've got their own kind of shorthand, a secret language to describe exactly what's going on. And that language is all about chemical equations. Honestly, the best way to think of them is like recipes for chemistry. They tell you exactly what ingredients you need, the reactants, and what you're going to make in the end, the products. But here's the thing. There is one golden rule that every single chemical recipe has to follow. It's called the law of conservation of mass, and this is a big one. It basically says you can't create or destroy matter out of thin air. Whatever atoms you start with, you have to end with those same atoms. In chemistry, there are absolutely no disappearing acts. And that is exactly why we have to balance equations. It's not magic, it's more like a fun logic puzzle to make sure our recipe follows that law. And while there are a few steps to it, the goal is always the same. Make sure you have the exact same number of each type of atom on both sides of the arrow. All right, so we've got the basics down. We know what reactions are and how to write the recipes for them. Now for the really fun part. It turns out that most reactions you'll ever see fall into one of 5 main categories, and I like to think of them as having different personalities. First up, let's meet the matchmaker. This is a combination reaction. It's really simple and sweet. 2 or more reactants come together, and, you guessed it, they combine to form one single, more complex product. A perfect real-world example of this is when you take calcium oxide, also known as quicklime, and you react it with water. They literally combine, they join together to form just one new product, calcium hydroxide. It's as simple as that. 2 things become one. So what's the opposite of the matchmaker getting things together? Well, it's the breakup, of course. This is what we call a decomposition reaction. This is where one big, complex compound just decides it's had enough and it breaks down into 2 or more simpler little pieces. So in a decomposition reaction, you're always starting with just a single compound as your only reactant. For example, if you heat up some calcium carbonate, it'll break down into calcium oxide and carbon dioxide gas. So one reactant becomes 2 products, the exact opposite of a combination. All right, get ready for some drama. Now we meet the homewrecker. This is a displacement reaction. In this scenario, you have a more reactive single element that comes along and literally kicks a less reactive element out of its compound so it can take its place. So here's how this plays out. Imagine you drop a piece of a reactive metal into a solution that has a less reactive metal in it. The more aggressive element basically just muscles its way in, kicking the other one out. A classic lab example is dropping a piece of zinc into a bright blue copper sulfate solution. The zinc takes over, the blue color starts to fade, and you see solid copper metal get booted out of the solution. Okay, after all that drama, things get a bit more civilized with the partner swap. This is a double displacement reaction. Here, 2 compounds just meet and
They trade partners. It's kind of like a square dance. Everybody switches, finds a new partner, and you end up with two completely new compounds. For instance, if you mix sodium sulfate and barium chloride together, they just swap their other halves. The sodium grabs the chlorine, the barium grabs the sulfate, and this often creates a solid, which we call it precipitate, that literally falls out of the liquid, kind of like that cloudy white barium sulfate you see forming right there. And finally, we've got the giver and taker, also known as a redox reaction. This one is all about an exchange. One substance gains oxygen. We call that oxidation. At the exact same time, another substance loses oxygen. That's reduction. They are an absolute package deal. You can never have one without the other. Phew! Okay, let's do a super quick recap of our 5 personalities. We have the matchmaker, where two things become one, the breakup, where one thing becomes two, the dramatic homewrecker, the polite partner swap, and the giver and taker. This little cheat sheet here is a great way to keep them all straight. Okay, so we've met the whole cast of characters. Now let's see them in action out in the real world. You know, not all reactions are some big flash in a test tube. Some of them are slow-motion dramas that unfold over days or weeks or even years. And you've definitely seen these two before, corrosion and rancidity. Both of them are just types of slow oxidation. Corrosion is that slow deterioration of metals, like iron turning to rust when it reacts with air and water. And rancidity, that's just the oxidation of fats and oils in your food, which leads to that stale taste and smell in old chips. But the cool thing is, because we understand the chemistry behind it, we know how to fight back. We can paint metal surfaces to keep the oxygen away. We can store our food in airtight containers. And chip companies, they even flush their bags with nitrogen gas to push all the oxygen out and keep those chips perfectly fresh. So what's the big takeaway here? What does this all mean for you? Well, understanding these fundamental rules isn't just for scientists in a lab. It's actually like gaining a superpower to see the invisible forces that are constantly shaping our world. Because chemistry isn't just in a textbook somewhere. It is happening inside you, right now, as you digest your last meal. It's happening inside the battery that's powering whatever screen you're watching this on. You are literally surrounded by and powered by these incredible constant chemical reactions. And that brings me to my final question for you. Now that you can kind of see this invisible world of chemistry happening everywhere, which everyday chemical reaction, I don't know, maybe cooking an egg or lighting a match, which one will you never look at the same way again?